My first judge when I reviewing a paper, right? If this guy know what they are doing and they know how to present it correctly. Then we talk about other things, right? So SE2 imaging, as I say, if you have charging sample, this is your best detectors, this is your friend. And I show you boron nitride. I think just now I talked to somebody who work in boron nitride. Is your student, right? Yeah. Boron nitride is the next generation graphene, I think. And this kind of sample, you can take the zoom out view, or you can take the zoom in view where you can see the surface detail and you can see the depth of field. Right? All this you can take within a frame. Right? Three low, my rule, three low KV, low voltage, low current. Low KV is voltage, low working distance, right? Three low. I love the next image. Okay, you see this. This is a silicon oxide nanoflower, sub-assembled. If you want to have one single flower like that, you cannot sprinkle. You must use sprinkle. You can see very clearly. And in the bunch, arranged properly, or this single. Right. If you are reviewing paper and you see this image, you will likely to pass the papers, right? Yeah. This is a very simple materials, but when you present it nicely, it will give you a different feeling. These are the aluminum oxide. I bring this sample with me today. Hopefully it doesn't damage on my way to from Singapore to Delhi. Hopefully, but you can see that all these are actually carbon monomers. Very detailed, very fine surface. Right? Magnetic sample. So when we tilt and rotate our sample, we are the only microscope in field that can do this. These are iron oxide magnetite materials, and it was assembled, sub-assembled. So each of these spheres is only maybe you see the scale is 100, probably 1 or 2 nanometers. Okay, they assembled into a big sphere, and you see no distortion at all. These are very strongly magnetic materials. No distortion. You can see very clearly. Because not Prof was asking about that, so this is the magnetic samples, Prof. Self-assembled iron 3 oxide, magnetite. No distortion. This is the military grade magnet, NdFeB, neodymium magnet. If you know neodymium magnet is a densest materials, very strong magnet. We can see it no problem with different detectors. Right. ESB. This is how the ESB works. The second electron will be repelled away, right? Then we can see. So this is 0 fault. We can see the sense of topography. That one totally flat. Same. Okay, different feeling. Right. And this one you can do very fast because you position it correctly. Take. You have 4 in one picture.
So the first one and second one in different position.
No, same. You can see this one is all the same position. See?
What is the difference?
The secondary electron is gone.
Sir, also the detector,
Yeah.
the detector that we are using on the first one and the second one is different.
Detector is different.
Yeah, so the first one is the
Inland.
inland ACE, second one is the energy selective backscattered electron detector. So both are in column detectors, but first one is for the secondary electron and the second one is for the backscattered electron.
Then how to compare this and this is basically the ESB just a further away. So the amount of SE they can reach the ESB is actually very less away.
There's a contrast difference when you increase the grid voltage.
Okay. Firestone. Firestone is basically if you have a lighter, there's a spark, and we try to do this and we put our sample holder there to catch the spark. This is what happened. This is the spark, the firestone. Alright? You guys, when you want to practice on this, you can use these techniques actually, but I don't know how you can light a cigarette in the lab, but like a small spark, and then you catch the spark. This is what you see. Same sample, BSD outside the chamber, and ESB is the same backscatter detectors, but you have different filling. Can you tell the difference? I don't know. The projector on my computer probably not do the justice to the picture, but you will have a different information. Yeah? So you need to judge, and when you want to send it for publication, you need to choose which one, and depend on what story you want to tell, you can choose a different sample. This is a zinc oxide materials, inland and ESB. You will feel that inland is more protruding the particles compared to ESB at 0.4. But when we do the even at 204 it's totally flat already. Yeah. And this one is a pure zinc oxide, but if you dope the zinc oxide with some other things, for example some rare earth materials, it will appear very nicely in this picture. But of course this is not the best sample because only zinc oxide, but if you have some other materials, some other metals, it will appear very nicely. Field of view, we can look at 12 mm, right? We even have a solution now that we can extend the chamber so we can see the whole 10-inch wafer. 10-inch wafer is about 30 cm. We can see the whole wafer in the chamber. Channeling contrast, I will leave it for tomorrow if we have time to discuss this. But this kind of image that what we want to see, we want to look at the linear dislocation, we want to look at the screw dislocation and so on. Alright? Cathodoluminescence, if your particle will, your materials will give out some light, we are able to capture it. Channeling contrast, these are just how I taught you about the.
See, you rejected this particular system though, that if you want to upgrade the system, see it's possible to attach.
20% commission on that. No, just okay. Yeah. These are really nice pictures. You can see the surface contrast. You can see the depth of field and so on. Tilt compensation. So sometimes you tilt the samples. There's blurry, but just with tilt compensation you can see it very clear. I mean, this is one of the few methods that you can use. Okay, let me spend 1-2 minutes on in India. We can share the same models, right? So no matter the sample come from me or from her, I can run on my space. He can run on the. This is another sample, right? Semiconductor. Anybody working on semiconductor materials? Here, which one is source, which one is drain? Yeah. You ask me, I don't know. But he said based on the this one, and this the third one.
Yeah.
Yeah. Okay.
And the feature.
So you can tell the difference. Have a difference, right? Nano FIPI, unfortunately, we don't have Nano FIPI here in this facility. But if you're working with biological samples, fibers, you can see things clearly, right? Pigments and so on.
So it is variable pressure.
Yes. Okay. I will end the first part of the presentation with this quote from our user. Actually, they are our user in Harvard University. What he's trying to say is very simple. Microscopy is so advanced. It's I will say funny things that we can do with our microscope that you might not be aware of. Right? Our software, SmartSense, allow us to do macros. Macros basically some instructions, some workflow that you have in your head, and it becomes your standard operating procedures. So you can create this in the SmartSense. So later, if we have time, we can show you this in the tools in the software. But basically, we can write our own script, right? And this is really easy proof. I have no programming background, but we can write a simple macro like this. We call it a start SEM. So this macro, for example, is a macro. So there's a lot of steps. and all this will be summarized in one button, right? So when you click that button, it's supposed to do all this sequentially. Right? For example, this one I call it start sample. Is that if I'm coming to run my samples, I want everything back in 0. The previous user will do some, I don't know what, right? I want everything back to 0. So I will create this macro and I run it. When I run it, everything back to normal. Then I can start my usage. So if you're working on particular samples that have requirement of particular scan speeds or to corrections or image analysis and so on, you can create a macro also. For now, you might not understand what I'm trying to tell you, but when you use equipment more and more often, right, you will create your own set of macro. Like me myself, I have my own set of macro that I've already prepared. Then I can just copy paste fast to the machine and I can use it. Alright, so these are the capability that our software offers. So you can create your own function. These are the few steps, and yeah, that's what I missed earlier. Now I want to go to topics that I really like. It called third-party tools and accessories simplified. So I try to explain different topics. Every topic 7 slides, no more than that. So it's a very summarized version. And of course, if you guys have a question on the tools, on the different accessories that I'm going to show you, we can discuss this. Raman spectroscopy, right? It started by this gentleman, Dr. C.V. Raman. And basically, our equipment, this is our SEM column, this is the Raman column, and actually our sample between the SEM and Raman. We use SEM to find the locations. You have big sample, you want to know the Raman spectra of that particular. Anybody not familiar with what Raman is? Raman. So Raman spectroscopy is actually a technique for us to find the functional groups, the fingerprints of materials. Right. So if you're working with polymers is the notoriously hard to do because so many functional groups, right? So Raman allow us to figure out what is the structures of the polymers, for example. And when you have other carbon materials, you want to know carbon is single bond, double bond, OCO, or in whatever C double bond, C double, C triple bond, C, and so on and so forth. You want to know. Raman and FTIR is a technique. Raman and FTIR actually are quite a similar one, but just inverse of each other. So you can use Raman or you can use FTIR. So our equipments can combine with Raman on the chamber. So you don't have to buy another Raman unit. So as you can see, the sample will move from the. I have the video. So, yeah. So this is our FESEM chamber. Then you can move to the Raman chamber. Alright.
We don't have this in our,
No.
but it can be upgraded. Can we?
It is upgradable on this system.
Yeah, it will come.
Yes. No, I'm not trying to sell you anything.
No.
They don't know I'm preparing this presentation, but what I'm trying to say is that, you can do beyond imaging. That's what my purpose is. Don't worry, I'm still an academic at heart. So if you shoot a sample, okay, you shoot a sample with light. In this case, it's a laser. They will give you two kinds of scattering. Okay, one is a Rayleigh scattering, which is the most of the signals, but you have a small amount of what we call a Raman scattering, and this Raman scattering is result of the interaction of the laser with your materials. So is the fingerprint actually. This one, 99%. We don't want it. We want the small amount, right? Of course, we can choose different type of laser. Whatever I listed there, we have. Okay. I mean, depend on the Raman. Because Raman itself, you have many suppliers. We work with all of them. So depend on what supplier you want, we can fill it for you. There's no issue. This is just one of my recent published paper on how we use Raman to explain the carbon range for the materials, and we can tell information from the Raman spectra. For example, we can take the fingerprint, the materials identification, from the X and Y, the X direction movement. When every bond shifted, we can tell about the compression, tensile stress or strain, whether the material is under stress or not. Intensity, and we can tell a crystallographic orientation. We can tell about the crystallinity from the full wave half maxima, the bandwidth, and intensity. We can know how much, right? The more intense one, meaning we have more of those things. So all this information are available. So I'll give you a sample. These are the video when we go from Raman to the electron microscope. So
When we are translating the sample, so we will get back to the same spot.
exact spot. Yes, sir. Yes, same ROI. Okay.
How it gives the crystallographic orientation? Please come back to
Yeah.
this.
This one.
Yeah, the crystallographic orientation.
Okay. So it's a whole semester course, but what we're trying to do is that we're changing the laser polarization. So laser is basically the light, right? We can polarize it, and the intensity will change. Alright? So by knowing that how much we polarize the laser, we know which direction we're talking about. So that's how we can get the polarization. But I mean
But there are many samples, many crystalline samples which are not Raman active.
yes.
In that case, how it will work?
Yeah, of course the caveat was this sample must be Raman active, and yeah, this is the benefit of Raman compared to IR. IR we can do the same thing. We can get the footprint, the fingerprint of the materials, but Raman have this some sort of advantage. But I mean we can go into details of it. And the things is we have the we can see the microscope, we can see the Raman, we can overlay the image, and we can get the Raman spectrum as well from the same sample. Give you another example. Yeah, same sample, we can get all this information just by translating it from. And the good thing is, the ROI, the region of interest is fixed, so you don't have to look again from your sample.
One thing I have still doubt
Yes.
that principally or physics wise, Raman is for the detection of local structure.
Yes.
Local,
Yes.
not the global. Global is for the X-ray and some stuff.
Yes. Yes. Of course, we have.
So if it is local, then how the crystalline structure will be determined by Raman?
Okay.
That is the main thing what we taught in MS final year student, difference between Raman and XRD.
XRD. Yeah.
Yeah.
XRD is
Because XRD is okay, it gives
It's a
the
bulk method.
global structure and the crystalline.
Yeah.
But Raman will give you the
the
local
locality.
structure.
The locality.
Right.
Yes.
So how you say that it will give the crystallographic orientation
No.
and crystallographic orientation is a global structure.
It's-
not the local.
No, the local. We won't be able to tell you the whole crystallographic orientation of that. No.
No. Okay. Very specific zone.
Yes. Yes. For Raman, yes, you're right. Of course, we have XRD, we have
Yeah.
XPS and
Yeah.
other methods. Right? Yeah. Sorry. So in the typical setup, we have FESEM, we have Raman, and we have the EDX. So we can do a 3 calibration, a multi-model kind of setup on this, right? And talking about brand, of course, you recognize the Renishaw, the Horiba, the Oxford, and so we can work with all the brands. There's no issue at all with compatibility. So we can use their own software in our tools, and and we can get the same thing. Any question on Raman before I move on to the next one?
So
Yes, please.
that lenses will be same for both
Raman, there's no lenses. It's just we shoot a laser. We can choose the wavelength and intensity of the laser to the lens. Yeah. But our SEM system.
Objective will be there.
Yeah. Oh yeah, for the okay. For the Raman, the Siemens.
Raman spectrometer, like rings or whatever, that can be assembled.
So, sir, in the case of like ATSM, this is confocal Raman testing. This is a microscope, confocal microscope with lasers basically and optics. So it can be integrated in the chamber as well. So we have the capabilities to integrate in the chamber.
Normally we work with Renishaw or Vitec.
We take,
Yeah.
we take.
Yeah.
We have a special product also that is RISE, Raman integrated SEM image.
What I'm trying to say is, if you buy the Vitec or Renishaw, this is the
Already have
yeah.
the standalone system.
Yeah, you have the standalone. We have an integrated product with everything.
The standalone, the problem is you need to find your spot again.
Yes.
We can predict the properties, and when we learn certain properties, we can alter the structures, right? Then the whole premise of this. So if you are material scientist, you're working with all these mechanical properties, you know that sometimes when you synthesize the materials, we need to do it properly so that we can have specially crafted materials for certain applications. So in Zeiss, we can work on this. So we work with a company called Diben exclusively on in situ tensile. So this one can do a tensile, they can do a compression, it can do the bending, right? So these two can be inserted to our microscope as well, right? And when we combine with EBS and EBSD, that makes the thing very interesting, right? We want to see how the grain changes and just before fracture and so on. So we have our own software that I don't want to go into details, but we can control mostly everything, right? We can do it in the flat, or we can do it in the tilted 70 degree. Why we tilted? Because we want to see the EBSD at the same time. So we can do all this. And just give you a flavor of what we can do is that, for example, this in situ mechanical testing, we can choose a different ROI, right? We can see a different ROI and we can see what happened during the tensile, right? We can take a video out of it, and nowadays journal publication, we also need to submit some videos and stuff. This is the good visual, right? To catch. So we can choose different kind of load, very flexible, from 200 newtons up to 5 kilonewtons. We can play with the temperature. Here we started at 100 degrees, but I think there are something that can go beyond that. 1002, I think it's possible. 1005, somebody asked, but we scared because 1005, then all our parts will be melted, right? The inside the micro. So our recommendation is to go to up to 800. And when we say 800, actually we can do a lot of things already at that kind of temperature, right? Pre-tilt is possible. Dual motor design. So we pull from two directions, and we can do a very accurate because of the dual optical. But all these belong to this company called Diben that we are working closely with. So I will show you one example when we are doing a stress strain experiment. So basically we keep pulling it, then you will see the EBSD map changes. As we go for higher tension, you can see the grain getting elongated in certain directions. For example, dislocation form, right? Even before fracture. So we can get the SEM image, we can get the EBSD, we even can take the ECCM and different tensile conditions. Any questions on these techniques? Okay. These are the things that I'm very excited about. I'm an electrochemist myself. I work with catalysts on battery applications, and I wish I had this tool during my PhD. My life would be so much easier. So basically, we can take out, we can put this thing. This thing is only about this size. So just to include a very small chamber that we can introduce. And it's actually, the idea is coming from the battery episodes, alright? From battery. What we are trying to do is, we will have a different electrochemical cell. We assemble it into this tool, right? We can do it in a glove box if needed because of the sensitive nature of the materials. And we assemble and we put it under the SEM. We even can connect our supply to it. Alright, so what I'm trying to tell you is that we can do electrochemical experiment inside the FESE. What kind of experiment we can do? We have 3 different types so far, but the field keep evolving. We will learn a new thing. So it could just be a very simple chamber, like what Ma'am said about we can put liquid inside the things that we can observe. And when we say liquid, this picture doesn't do the justice because it seems like a lot, but it's actually a couple of microliter, very small amount. Alright. We can see the morphology, composition, reaction mechanism in the liquid phase, and we can see the chemical reaction under E-beam. For example, some materials are sensitive to E-beam, then we shoot, then we can see what happens. Right? For those who are in electrochemistry, I remember the lady in the we have the standard three cells configuration, right? The reference electrode, the control, the working electrodes, and we really can monitor what happened, during the, for example, cyclic photometry, right? We ram up the voltage, then we come back, right? Before this, we can only see the graph from your meter, but now we can really see what is happening, right? So this is very cool stuff. We can introduce a different electrolyte, a different electrode system, and so on. And we can introduce the power supply to give the whatever voltage you want to the system. The third one is microfluidics. This one actually to observe how the materials behavior under flow. Right. So for those who are working on microfluidics, we have this. But to be very honest, I'm not very familiar with that because it's not really my field. But it's something that we can do in the things. So to give you a sense of what we are talking about, the liquid thickness is only in the nanometer range, 100 to 2000 nanometers. We are covering it with this material called a silicon nitride film. So it's a very thin film, alright, to cover the materials. And the chamber size is, you can see it's sub millimeters. It's 1 mm kind of thing. Liquid volume in the microliter. We can put a 3 electrode system. Electrode we can choose between the silver, platinum, carbons, and of course, reactive electrode is not there yet, but who knows, in the future we can make some reactive electrode also, like copper or something. Alright, then for the microfluidic is as follow. And the chip size, to give you the context, is 3 times 3 times 0.1. The thickness is only 0.1 mm. So I hope you can imagine what is the shape looks like 3 by 3, right? Like 3 mm times 3 mm, then the times 0.1. Very, very small. Very small. Okay, I can tell you about this, but I better show you what is the result that you can see. So you can see. So this is your battery. You remember we do the charge-discharge things, and after a while the battery will become obsolete. This is what happened because there is a formation of the lithium. You still can see it start to form lithium oxide nanosheets on the surface of the battery. Right? Yeah. Is the video clear? Yeah. Okay. This one. Another example: zinc ion battery. This is the electrode, and you can see the formation of when the zinc in the electrolyte is reduced, you will form some zinc on the surface. You can see some dendrite formation. It's coming. You see? Yeah. So that's to show the reduction reaction when zinc reduced to form a zinc metal. HER, hydrogen evolution reaction, hydrogen economy. We want to find the best catalyst to produce this hydrogen. So for the first time, actually, you can see the formation of hydrogen on the surface of the electrode. with the video play. I will play both video. You can see the bubbles start to form.
This is very impressive. And just to take this forward, you showed us about hydrogen evolution. So there is also a lot of talk about this hydrogen embrittlement and all.
Yes.
So those kind of studies also we can maybe not.
Yes, we even I'm just thinking very widely, right? So hydrogen embrittlement, right? Then we want to see the stress formation, the cracks formation. We can even combine it with PCCI for example. I think it should be possible.
So if we can build up say a small cell,
Yeah.
where you showed earlier that big tensile specimen you showed
Yeah.
us, right? So if we can just expose very small region of that tensile specimen to kind of hydrogen charging, and then this is so impressive. You are seeing
Yeah.
carbon forming.
My last project before I left academics is on HER catalyst, and I wish I had these tools before. Then it really will. Last one is my favorite. It's a nano bubble. So we published this paper together with our client in China. So I will play let's say the middle video first. The middle one, you can see that the bubble formation and the big bubble eating to the small bubble, surface tension, and all this. We have the proof now, right? And this is a physics paper, right? I show you the top video now. The formation of the bubbles. This life, then the big bubbles will eat, so-called eat the small bubbles. Yeah. In interfacial chemistry. The bottom video. Can you imagine we can do this in our microscope? Really amazing. Yeah. Okay. Electrochemistry. Any questions, feedbacks, thoughts? Yes, please.
Sir, suppose I have
Cheaper than the liquid nitrogen. Of course, you can have the cryo stage with the liquid nitrogen and so on, but it will be very expensive. But we use this. Yeah. We use water to lower down the temperature, and this is a plus minus of a cryo stage. So you want Peltier cooling. Peltier probably is cheaper, and we work with this company called MeBuild. So MedBuild, sorry, MedBuild. We can buy off the shelf from them, and we can use it in our microscope. This is just a different things. But again, for today, this is not important. The details is not important. I just want to show you all the, Yeah. So when the freezing happens, then we can see some sort of morphogenesis. I'll show you this video. So we lower down the temperature, then the ice start to form, and the morphology will change. So this allow us to do experiment below 0 degree. So just now for biological samples, this could be one alternative that we can freeze the thing -60 for example, -70. It precise control of temperature. Then we can do things. This is the chicken nugget. This is the chicken nugget that we did. So yeah. So basically, we go to the lower temperature and try to fix the biological samples. We consider this biological sample because they have fibers and stuff, and they can from the SEM. So for this project, actually we build the AI model for them. So after they scan the picture, they run it through the models. Then they know, okay, this is 60% meat, or this is 30% meat, whatever. So you have different grade of nuggets, for example.
So, this nugget, increase the protein for the measurement or without protein?
And
Protein or
we are the only company who doesn't sell sputter coater as a basic configuration. You buy from other company, they will automatically offer you a sputter coater. I hope we don't offer them sputter coater.
No, they have sold.
Maybe
You-
third party.
They have sold them.
Okay. Normally we don't offer it as a standard.
Then why you have
I'm sorry.
Third party probably.
no? But if it is not required, we can with that money we can purchase other systems.
Exactly, because this system is, you can use it such low accelerating voltage. It's
But
very
But this
good.
is with full distance.
Yeah, for the Spartan Quarter is not too expensive to be honest. Maybe $10,000 something like that.
For Indian people, everything is.
I'm sorry, I didn't. Frozen fruit. So this company also go to the extent they want to calculate percentage muscles in the chicken meat they use to make.
So in the market, what kind of thing actually they are interested to see?
They want the customer to have a same experience. Let's say I fried a bag of nugget. Everybody will have the same experience. Consistency of the product. They want to know the percentage of muscles. They want to know how much meat are there, how much flour was there, starch, and so on. So all these companies really go to this line to ensure that the experience,
quality is-
the nugget you experience is. So they, I remember this project because they supply us with the chicken, the raw chicken. They supply us with the cold nugget, coated with the flour before and after frying, and they want information for every step. And in between, we managed to sell them a couple of our iPhone
Good for you.
Every nugget we put a microscope then.
In Zeiss, we did our chicken rights. That's what we always say, right? Yeah, we did our chicken rights. Yeah. So this is maybe the fourth technique and maybe the final techniques that I can share with you. So I hope this session will make you think that the different possibility. So it's not only imaging tool, you can do much more than that. And if there's any technical question, me, Dr. Subanshu, our sales people, sales colleagues, and then